Let's work another problem of conservation of mechanical energy. In this case, we have a car that can move between two compression springs. Each spring has a different spring constant value, and we initially compress the car against the spring that is stronger, and that means we will compress the car against the spring with the highest K, because remember, the spring constant measures how stiff is the spring. So the stiffer the spring, the higher the value of K it will have. So that means the spring on the left is the stronger, and the car is initially pressed against that spring. Another important piece of information is that the car moves without friction. And that's important because that means the mechanical energy will be conserved, which means that the mechanical energy will be distributed among the kinetic energy of the car and the elastic potential energy on the springs. So initially, the car then is compressed against the spring on the left, and the spring we know is compressed by 3.2 centimeters. So if we call this spring 1, we would have the compression for spring 1 is 3.2 centimeters, which is equivalent to 0.032 meters. The mass of the car is known, and this figure shows then the initial configuration of the system. The system, by the way, in this case will be the car, which may have kinetic energy, and the two springs that might store elastic potential energy. The final configuration would be when the spring on the right is found at maximum compression. So the final time, we will have the spring on the right with the car next to it, and we would like to find the maximum compression that the spring on the right will experience. So we can write the conservation of mechanical energy . So we have the kinetic energy of the car at the final time. We have the elastic potential energy at the final time. That will be in one of the springs. In this case, since the car is not moving in the vertical direction, the gravitational potential energy will be constant and won't be relevant in this problem. Whenever the gravitational potential energy is constant, we don't need to write it. So on the right side, we will have the equivalent, but now for the initial values. We can simplify even more this equation if we realize that when the springs are at maximum compression, the car will be instantly at rest. So, since the initial and final times springs are compressed at maximum, the kinetic energies will be 0. And we end simply with the potential spring energy. And we know the formula to calculate the potential spring energy. At the final time, the car is pushing against spring 2 on the right side. At the initial time, the car is pressing against spring 1 on the left. And from here, we need to find the compression on the spring on the right, or the compression delta L2. The factors of 1/2 will disappear because they appear on each side of the equation. And we can take delta L1 squared out of the square root to get, and we are ready to substitute values to finish this part of the problem. And we can write the result in centimeters as well. And this is the maximum compression of the spring on the right. For part B of this problem, we need to find the maximum speed of the car. So we need to choose an initial moment and a final moment. And the moment when the car is moving between the two springs without contact of any of them will be one of those times. So let's choose as the initial time the moment when the car was pressing against the stronger spring on the left side. So we have that this initial time that the compression for spring 1 was 3.2. That's the maximum compression of that spring. And we know that when the spring is at maximum compression, the speed of the car will be 0. So the initial velocity of the car is 0. At the final time, we will have the car moving between the two springs. So it will have some final velocity that will be different from 0. This is what we are trying to find. And the compression for spring 1, since the car is not in contact with the spring anymore, the compression will be 0. So the spring is completely relaxed at this instant. Okay, so we can write the conservation of mechanical energy. For the final time, we have kinetic energy, potential energy in the spring. On the right side, the equivalent, but now for the initial time. Now, for the final time, we already said the compression is 0, right? So the spring is relaxed. So at the final time, there is no potential elastic energy. For the initial time, we know that the velocity of the car is 0. So the kinetic energy at the initial time is 0 because the car is at rest. And the equation then simplifies and we get kinetic energy at the final time and elastic potential energy at the initial time. From here, we isolate the final velocity. The factors of 1/2 cancel because they appear on each side of the equation. And we are ready to plug in the values. So the spring constant for the spring on the left divided by the mass of the car square root multiplied by the initial compression of the spring. We get 1.9 meters second for the maximum velocity of the car. So actually the car is moving with constant velocity when it's not in contact with any of the springs, because since the car is frictionless, there is no energy dissipated by the force of friction. And that's all for this problem.